Hello and welcome back to the Deep Learning course. This week, we'll discuss how to quantify the uncertainty in the predictions of our neural networks, which is crucial if we need to trust our neural networks. We'll spend a good part of the videos on principles of Bayesian reasoning, using the example of Bayesian linear regression. And then we'll see how we can apply these Bayesian principles for neural networks. In this first video, we will motivate why we need uncertainty in deep learning, and we'll see what uncertainty estimates mean for classification and regression tasks. Let's dive right in. Why we need uncertainty in neural networks. The motivation for wanting to know how uncertain our neural network models are becomes clear when we consider safety-critical applications, such as medical diagnosis, autonomous driving, operations in space, or household robotics. Also, it is instructive to think about the fact that we are not just fitting deep neural networks for the sake of predicting the world, but for actually acting in it. And if we want to act optimally in an uncertain world, then decision theory is the right tool of choice. Decision theory is all about judging the probability with which certain actions lead to certain outcomes, and then judging the utility of those outcomes. Think about the autonomous driving setting. There's an uncertainty about what other cars will do next, and if we don't capture that, then we can't actually use our models to reliably inform our actions. So what is the state of predicting uncertainty in neural networks? Let's look at the classification setting first. So standard neural networks do output a probability distribution, namely there's a softmax distribution in the last layer, but this probability distribution is often not reliable. In particular, uncertainty should really grow away from the typical data that we've seen at training time in order to be useful in practice. However, in many popular types of networks, that is actually not the case. For example, there is a theoretical result that for ReLU networks, there are points that are very far away from the data, and the networks nevertheless are arbitrarily certain about these points. Deep neural networks can also be very overconfident for images that we as humans would clearly not recognize as belonging to any reasonable class at all. So these images here were actually evolved to be classified by a particular network with more than 99% probability to be one of the familiar objects used during training. For example, the network is really certain that, well, this here is a centipede and this here is a dragfruit. And to me, to the naked eye, this looks pretty much identical, and I certainly don't see these objects in there. So while these first 8 images here were evolved directly on a pixel level, these second 8 images here used an indirect encoding for the evolution process, namely a compositional pattern producing network that evolves more regular images. And for that encoding, for example, for a remote control here, you do see that there are elements such as buttons, but you would nevertheless not classify this as a remote control. So it's very easy to fool networks into classifying with a high certainty, and that is, of course, a big problem for practical safety-critical applications. For regression, the uncertainty estimates of standard neural networks are even worse because, well, they simply don't exist. A standard neural network only outputs a single value and no uncertainty at all. And again, we would like to have uncertainty predictions that grow away from the typical data that we've seen, as shown, for example, by this Bayesian neural network here in this plot. So here we have a regression setting where these blue crosses are the actual data points that we've observed. So for example, for an x value of -1, we have observed this data point so the y value is roughly -1. And in this plot, we also have the predictive mean of our Bayesian neural network and the predictive uncertainty band, here the standard deviation of this neural network, shown as this red funnel. And around the data points, the uncertainty predictions are very low. So, for example, here or there. And away from the data, the uncertainty predictions grow a lot. So even in the middle, between two observed data points, there is actually a data point here and there's one there. In between, uncertainty is large, and away from the data, it's very large. However, there are regions here where there is no data and the uncertainty is not large because, well, in order to fit this fairly extreme spike here with a lot of data, there aren't a lot of different alternatives for predicting in between. And that's why the uncertainty there is not very large. So this is a type of uncertainty predictions that we would want. And this week, we'll see several different types of Bayesian neural networks that can give us this behavior. Finally, I would also like to mention that there are different types of uncertainty that we can quantify. So in particular, there is the so-called aleatoric uncertainty, which is the intrinsic observation noise that we can't actually reduce. So as a way of remembering this term, alea in Latin actually is the dice, and well, this observation noise is exactly this type of noise that we get from throwing a dice. You can throw this as often as you want, and you still don't know what the next outcome will be. So next to this aleatoric uncertainty, there's also the epistemic uncertainty. And this is the uncertainty about the model. So that relates to our knowledge of the world, and as we obtain more and more data, we can reduce this part of the uncertainty. And we can actually express uncertainty about different quantities. We can express uncertainty about the true state of the world, and that is the epistemic uncertainty. But we can also express our uncertainty about what we will measure about the world. And that combines elements of the epistemic uncertainty and the aleatoric uncertainty, because it includes both the uncertainty about what the world will actually be like, and then on top of that, what the noise will be when we actually measure. All right, that brings us to the end of this video. And as always, I'd like to leave you with some questions. I encourage you to pause the video here and think about them to activate the material. Thank you, and I'll see you in the next video.